Alright, welcome to this practical tutorial from Clinical AI Academy, which is the first practical tutorial on building clinical AI tools from scratch. Today we're building an intracranial hemorrhage detector. So my name is Ahmed Nazal and I'll be taking you with me in this tutorial. So in this session we will build a simple but complete AI pipeline for detecting intracranial hemorrhage on head CT slices or head CT scans. So we will go step by step using a real dataset and a real code, and we will train a model that outputs a probability of hemorrhage for each slice. So the goal is to show that clinical AI is accessible and understandable even if you don't write code every day. So what we will do is, first of all, we'll introduce this platform, Kaggle, and then we'll touch a little bit on some clinical background like CT brain imaging and intracranial hemorrhage to understand the problem that we're having, and then we'll explore the dataset that we will going to load, and then we'll build a pipeline using pytorch. So this is a library for deep learning and used in preparing clinical AI tools. So we will use some of the functions that are in this library, and we'll train two models, actually one that is a dummy model, so like a tiny convolutional neural network from scratch, so we see like the layers, and then we'll train the ResNet 18 model to show more realistic performance, and we will evaluate the performance using things like loss, accuracy, and receiver operator curve and area under the curve. Compare that to accuracy and see which one is better, and then we will even look at some slices and see the predictions and how compare them to the ground truth, and then we'll even have a heat map using GrandCam to kind of show us how the model reached predictions. I think this is important to touch on also, like the principles behind this tutorial is the idea to show that anyone from all backgrounds could build AI tools, like clinical AI tools, regardless of their background, regardless of your education level. So you really don't need to be a coder. I'm not a coder. I'm trained as a medical doctor. What really matters right now is actually like your ability to kind of understand the problem and try to find a solution to it. So it's not the coding, it's not the language of coding that is the bottleneck, but it's like how you approach it. Second point is that you only can understand it is only when you can build it. So that is the idea of learning by doing, because you make mistakes and then you fix those mistakes, you play around with the code and then see what changes and so on. So this really builds your muscles. So we run real code, we'll load real data set of real patients, and we look at how to make sense of the results that we have. So by the end of this tutorial, you will have a working intracranial hemorrhage detector and know how to use this approach to other clinical tasks. So let's begin. I'd like to begin with first introducing Kaggle platform. So what is Kaggle? Kaggle is used for data science and machine learning competitions where users can compete to build the best models. It also serves as a platform for learning. That's what we're using today, with datasets, code, notebooks, and tutorials, and for collaboration. So yeah, you go to it, you log in, and you land on a page that actually looks like this one. If you open a new notebook, then you end up on a page that looks like this one. The next thing before we load the dataset is I want to kind of introduce the background for the CT in general, or CT brain imaging, and give some clinical background on intracranial hemorrhage. So computed tomography CT is the primary imaging modality for acute evaluation of the brain. Why? Because it is fast, it's widely available, and highly sensitive to differences in tissue densities. So this is on Wikipedia, and you can see that those are slices from inferior, like from below to top of the skull. And I guess like each slice has a specific thickness that the department or the radiologist can set. So this is a CT scan of the brain. So there are different densities, like the different colors as you have seen on this image. So this is the bone, for example, and then you have the white matter, and the gray matter, and so on. So the densities measures the X-ray attenuation. If it hits like a dense thing, like in its way, like the bone or a metal object, then it will be white, and then black is the air. And it is measured in Hounsfield units. Why? Because this Sir Godfrey Hounsfield is the guy who developed this technique. He's a British electrical engineer and a Nobel Prize winner for physiology or medicine. So yeah, and then those house field units are the measures that we measure the densities. So -1000 is very dark, which is the air, and then bone is like between +700 and +3000 house filled units, which is very bright. So for our case, which is intracranial hemorrhage, it's bleeding, so it's blood, and fresh blood is around like 50 to 80 or +50 to +80 house filled units. So this is hyperdense compared with normal brain tissue. And the difference in attenuation allows for fresh intracranial hemorrhage to appear bright and relatively easy to detect on non-contrast CT. So if you're giving contrast, then the contrast will be bright. So this is not suitable for detection intracranial brain hemorrhage. So you need to have non-contrast CT. And you can do the windowing. So you basically change the values of those house field units, and the brain window shows the brain in the best way is between 40 to 80. So as I mentioned, acute blood appears hyperdense, so bright, on non-contrast CT because fresh hemorrhage has higher attenuation than surrounding brain tissue, primarily due to hemoglobin's protein and iron content. Good, so those are the basics. Let's see what is intracranial hemorrhage. So intracranial hemorrhage refers to bleeding within the skull, and it comes in several types depending where it accumulates. So type of brain hemorrhage, here you have the skull with this diagram, then you have the dura mater, then you have the arachnoid mater, and then you have the pia mater, which is the one that is closest to the brain tissue, and then you have the brain tissue. So you have the epidural hematoma, which is extradural, looks like a lens, and then you have the subdural, which is below the dura mater, and it looks like crescent shape. And then you have the one that goes into the arachnoid space, those guys here, and then the one that is intraparenchymal or intracerebral, so in the brain tissue. And you have sometimes intraventricular, which is in the ventricular brain system. So those are the subtypes of the brain bleeding or brain hemorrhage that you get when something like this, when bleeding happens inside the skull. This is dangerous, one of the deadliest forms of stroke. The patient comes in with stroke-like symptoms, so weakness on one side, for example, or loss of vision, and so on. It really looks very similar to infarction, which is loss of blood supply. But in this case, it's bleeding that is pushing on brain tissue. But it's very important to differentiate between those two things because the therapy depends on this differentiation. And this differentiation needs like CT as soon as possible. It is time critical. The intracranial hemorrhage is time critical. Why? Because it could lead to intracranial pressure increase, and then herniation of the brain tissue, and then mortality and death. So let's look at different CT scans with intracranial bleeding in them. So this is an epidural hematoma. You can see how it looks like. It looks like a lens shape or lemon shape. This one, hyperdense, so looks brighter than the brain tissue here, but less bright than the bone. So this is epidural. Extradural. The other one we have is subdural. It looks like a moon shape, brighter than brain tissue, but less bright than the bone. Different brightness in it because the time it took to accumulate in it. So some blood is fresh, some blood is not that fresh. And then what you have here is subarachnoid. You can see it. It's like in between brain tissue, but not directly in the brain tissue. So compared to brain parenchyma, it is more, it's brighter, but less bright than the bone. And finally is the intraparenchymal bleeding. You can see it's in the brain tissue itself with this whirling kind of shape. Alright, so with this we have the introduction to Kaggle and some background on what is a CT, the densities, and then the intracranial hemorrhage. And the next step is that we load or look for the dataset. So Kaggle has many datasets in it that you can load basically into your notebook. So this is called a notebook. I looked them up, so you could also look them up by searching here. So add input dataset. Then so this one is called brain CT images with intracranial hemorrhage masks. That's the one we want. So I kind of looked for suitable data sets. You have many of them, so you could then look for this one and load this one, brain CT images with intracranial hemorrhage masks, and just press this plus button. So this has in it files. Let's just look at it and see if we can understand the structure. So computed tomography images for intracranial hemorrhage detection and segmentation. It has like patient CT, so it has, I guess, so you have here the patient's files, and I guess it has like, we're going then to kind of investigate how many patients do we have. So this is the patient's file. So, and then you have the images here in the bone window, so you can look at that here and view it. So you have the bone window here for patient number 1 or 49. We have the brain window. As you can see, and then number 14, for example, it has also the mask of where the hemorrhage is. You can see there's a little bit here for the hemorrhage, bleeding. So yeah, so this is the structure of the data. Those are the raw images. You have the license, then readme file, and then you have, I think this is the weights of their training, and it's even like split data, but we're going to do that. And then this is labeling, so this is the ground truth. So for patient number 49, this is slice number 1, and they describe if it has intraventricular bleeding, interparenchymal, subarachnoid, epidural, subdural, or no hemorrhage, and fracture or not. So you see, like for example, for patient 49, you have 33 slices, and from those 33 slices, you have here there's a bleeding, so intraparenchymal in slice number 21, and then also epidural in the same slice 21 and 20, I guess, sorry, 21, yeah, 21, 20, 22 has epidural bleeding. The rest, most of the slices, they don't have bleeding, right? So this is important, so to keep in mind, and this is what's usually the case in medical data sets, that the pathological slices in this case is less than the normal, so that you end up with an unbalanced data set. So you need to take that into account once we are training our model, because we are dealing with an unbalanced data set. All right, so let's start by loading this data set that we have. Okay, before we do that, let's just choose an accelerator. Probably we're not gonna need it, so just to make it faster, and then have the first code that calls. Basically, this what it does, just goes to this directory and calls it. So we have here basic Python libraries that allows us to do the things that we are going to do, like for example calling this data set and then viewing the images with this function here, and then this will help us from sklearn do the splits that we need for the model, and then from torch we will use those functions that will help us just prepare the data that the model can deal with, and we will see in a moment. So let's just run that and see how it goes. So once you run it, it starts downloading those images in the dataset. So that's good. That means that we have this in our working space, and then it starts downloading the images, the files, and you can see here. It's not a big dataset, so it's good for this demonstration. The dataset is now downloaded on the workspace, but we have here an error. When you have like a new notebook, you have some of the very basic functions that you need already imported. We didn't have that, so we need this OS because this was not defined. So just like rerun that, and now it's working. So it managed, now it's downloaded, and now we have it loaded, kind of. We have the dataset in the working space, and we can now work on the dataset and start like building the structures that we will use that the model will use for like training. So those are what is referred to as the like using this dataloaders and dataset functions. So it prepares the data structures that referred to as tensors that the models can deal with, which is basically just like columns of data, of pairs, of the images, of the slices, and their label. So the next thing is we define this. So this section will build this image label list, or at least define the function that can do that. So it goes to the patient's directories and then patient IDs, and then into that patient IDs then we'll go to the brain and then take those slices, which is in JPEG format, and then pair that to the label from the one that we have from the truth, like of each, like the ground truth that was set by a human expert, like does this slice have a hemorrhage or does not have a hemorrhage, so positive or negative. And then this will collect that in something called all pairs, right? So we have this name glob is not defined. We need to define another thing. Glob here optimally should be done here. Just let's do that and see if that fixes it. Right, so exactly, we have now a total number of patients, 82 patients, and then we have 2,501 slices, 383 with intracranial hemorrhage, and no hemorrhage is 2,118 slices. So that's the imbalance we talked about earlier. So the next thing is do the split. So now we have loaded the data, we have the pairs, we know which ones, the slices that are positive, the slices that are negative, and then we need to kind of do the splitting of the data set. So this is the usual case, like when you're training, you do have training, your data set that you train your model on, and then you have the validation. Optimally, you will have like training, validation, testing, but since we are doing it at slice basis because we don't have enough patients, 82 patients, usually you want it on a patient's basis. So if you have enough data, you have like train, validation, and testing that data is something that the model will have never seen. But since we're doing it on slices, then you have a leakage, like of some slices from one patient and the other, so we're not going to do that. And just for practical reasons and education reasons, we'll just have it as train and validation split. So right, this goes like basically into takes this function that is a built-in function from sklearn, and this is just you use it for this train split, test split. And this is the idea that I told you. It's about thinking of like understanding the steps, like pre-processing, loading the data, then now doing this splitting thing. And it's not about the coding itself. So once you understand the overview, you really don't need to code that much. It's already done for you by others and that prepared those great libraries. So we have like those random seed is just like where it starts the model so that you consistently get the same results. So it starts at, for example, slice 42, let's say, or like data point 42 from this all pairs dataset that right now we prepared from the original dataset. And then you have a validation fraction. So you have 80% for training and then 20% for validation or testing, basically. But always keep in mind that then both of them, they are coming kind of from the same distribution. So you have this, it's not like something that you can go and deploy in real world situation. So random is not defined. Keep getting those not defined stuff. It's another import thing. Right, so right now we have split the dataset into train slices is 2000 and validation slices are 501. So you have seen before, like the total brain images were 2500. Yeah, so we have now done the data splitting, and next we're going to use pytorch, to do some pre-processing for us, which is basically look at those pairs and then put them in a similar size, and then normalize those images, then put them in a grayscale, then do all this data manipulation so that you make them more homogeneous, that the model learns better, so you improve your modeling, and then generate those tensor files or tensor structures that you need for your model. You define a class from this dataset like we loaded before, and then you want the pairs to be like an image size. That image size, we are not going to go augment them, like we do some data augmentation to increase the number of images, so improve also the model function. We're not going to do that. And then you return the length of the pairs that you have. You have the image path and the label that associates with the image path. So is it like, does it have bleeding, does not have bleeding? And then with this function, you use this image also built-in function to do it in a grayscale, and you do the resizing, and then you do the normalizing, as I said. And if you do any augmentation, then use torch, which is recalled or imported to build this image tensor, and that in parallel to it you have the label tensor. So I think we ran this, yeah, all right, and then we do some sanity check. So we set the batch size to 16, so it will take 16 slices every time that it goes through the training loop. And the images are size, each image should be 224, and you have 2 workers. This is enough for Kaggle, so that it does that a little bit faster. You have the train dataset, we have the validation dataset. It calls this function that we defined earlier that has an input of the train pairs, the image size, and augmentation. If it's true or false, we have it for training true, for example. And then the validation dataset calls the same function, but for validation pairs, the image size and the augmentation here. Then the train loader calls the dataloader function, which is we imported from torch or pytorch, and takes the train dataset, this one, as an input, the batch size we defined here, and shuffle that, and then have the number of workers, and then have the pen memory is true. So, and the pen memory is again another pytorch data loader option, which speeds up copying of tensors from CPU to GPU, so just to make it faster. Same we do for the validation loader. Load the data loader, you use the data loader with the input from the validation dataset that you defined here. So you end up with having a batch image of those dimensions, which is should be 16. So 1 here is stands for that we have 1 channel, since we have a grayscale images as CT scans, so it is 1 channel. If you have like 3 colors, then you have RGB, so this would be 3 channels. Height and width of the image, so this should be 224. So this is the tensor shape. So it's not 1 column, but it's like a 4-dimensional kind of matrix that's the batch image tensor shape. And then the batch labels shape is again one column of 16. So each batch is 16, I guess, slices, and then you have one column with each slice as a row. Label proportion mean we will end up having like how many of those slices are positive, like have bleeding in them. Let's see. So we have in this batch, like 1/16 is around this number, I guess. So we have one slice from this batch that has bleeding in it. Okay, so let's continue. So basically what we did so far is just load the data and prepare it for the models to accept it. So this is the structure that we expect. This is the size of each image, and then this is the channel of the colors, and this is the number of batches, so the number of slices that goes on for each iteration of the model. So next we will prepare the dummy convolution neural network before we jump and use a pre-trained or like a ready-made kind of neural network that is called ResNet 18. But before we do that, I'd like to touch on the human visual system. So let's just make that a little bit bigger. So how does the human visual system work? If like a radiologist is looking at a CT of a slice of a CT of a brain scan, we have this diagram here that shows visual tract. You have the right eye, the right eye, the left eye, and then the visual fields. This is the right visual field, and this is the left visual field, and then input light comes in through the eyes, and like the retina, where the optic nerve starts and then goes to the optic chiasm, and then goes to the thalamus, where you have the lateral geniculate nucleus, and then from there this relay station goes to the primary visual cortex. You can see that depending on where the light comes in, the information, so this is coming from, for example, right visual field and falls into the left eye, and then this information is carried, so the spatial information is carried in this tract here and continues into the left side, and then you have this information from the right visual field falling medially in the retina, and it's carried here and decussates, so crosses at the optic chiasm and then goes to the visual cortex on the left visual cortex. So here's the front of the brain, here's the back of the brain. So you could see that there are two kinds of information. What is going on here? What are you looking at? Say like CT of the brain scan in this case. And the other thing is where things are happening, like in the visual field. Are they on the right or the left? And this two information are carried, and the visual system or the visual cortex has to deal with them in order to understand them. So if you look at this tells us like after reaching the visual cortex, then you have different layers. So the visual cortex, then you have different like processing layers. So the basic features at the beginning, and then it gets added on until like an object recognition happens. And there are two streams, like one that deals with spatial information that goes dorsally, so the parietal, and then ventrally goes to the temporal lobe where like goes here. You have fusiform area and where recognizing faces, for example, and then those two informations, the brain puts them together and kind of you understand what's going on. So as you can see here, the retina, then the first lateral geniculate nucleus here, which is in the thalamus, and then goes to the visual cortex, the V1. So the visual cortex has V1, V2, V4, and then in this case inferior temporal cortex. So you could see that the complexity of the image, once you go through the layers, so what you're dealing with gets together kind of more and more. So this is the feed forward, and then there is also like backward information that goes and like a feedback loop. So this idea, this hierarchical structure, is what inspired the convolutional neural networks. So a convolutional neural network mimics the layered processing, and then each layer learns simple patterns similar to the visual kind of analogy, visual cortex analogy, edges and gradients. Then if you go deeper in the layers, more complex features are learned. The first one that did that very successful using images, real images, using this ImageNet dataset, which is millions of images, was the one called AlexNet, and this is the architecture from the paper. This is the figure 2 from the paper. So you have, this is the image, and you can see this is square, this is the convolutional sliding window, and then goes the first layer, and then you have max pooling, second layer, gets convolution, and so on. So how does that work? So if you have an input image of 5 by 5, each number here is like the value representing the pixel, like value of intensity of the pixel in the image. So you have like 5 by 5 here, pixels 1, 2, 3, and this one's 3, 2, and 1, and so on. So the convolution, you apply this convolution filter, it is a 3 by 3. So you multiply those guys here by those values, and as you can see here, so we took those 3 by 3 and then multiplied them by the convolution filter, and we sum them. So we multiply and then multiply 1 by A, and then sum 2 by B, and then plus 3 by C, plus 4 by D, plus, and so on. You get the sum of those values, and then you slide that to starting from 2, and you multiply and add, and then you slide by another one, you multiply and by add, and then you go down, and so on. So you apply this convolution filter, which is a 3 by 3 in this case, on all the pixels in the image. You multiply it and you sum, and you end up with a 3 by 3 output feature map. For example, this is the example. So these are the values of this multiplication and summation, and then use the next sliding window, and so on. So that would be what's going on in the first layer, and then you move to the next layer where you do the same thing. But before you do that, you apply something called max pooling. So why? It tries to reduce the spatial size of the feature maps, which takes the maximum value inside a small window, usually 2 by 2, and then moves that window across the image with like 2 steps. So the idea is reduce the image dimension so that the network learns faster, and then you focus on the most important salient features. Let's take that as an example. So you have this feature map from the first layer, and then you take from like 2 by 2 block, like let's say you take those 1, 3, 2, 5, or 1, 2, 3, 5. The biggest value is 5, so you take 5, and then you move to 1, 0, 2, 1, you take 2, and then 0, 1, 1, 0, you take 1, and then 4, 2, 2, 3, you take the biggest number at 4, and you end up with 5, 2, 1, 4. So you took the most salient number is 5, or the biggest number is 5, and you move on. So you reduced the features. We did the convolution first, and then took the output feature, and then you reduced that by the max pooling kind of in dimensionality, but you maintain the important like pixels or important information, and then you move it to the next layer. But we also need an activation function. So what we do is, or what is done, is adding this ReLU function. So let's read why we put a ReLU between convolution and pooling. So each block in a convolution neural network usually follows this structure: convolution, ReLU, which is nonlinearity function, and then pooling. So the convolution extracts linear sets of features by like weighted sum across local pixels. So on its own, this is a linear filter. So the ReLU turns linear filters into activated feature maps. So without ReLU, stacking more convolutions would still behave like a single linear operation. ReLU is what lets deep neural networks learn complex layered representations. You don't want to deal with all the information that is in the image, so you want to deal with, let's say, in that pixel, does it have hyperdense signal, like suggesting blood or not? And this is what the ReLU does. So let's just look, how does the ReLU look like? So it stands for rectified linear unit. If you have any values below 0, it makes them 0, and any values above 0 makes them 1. So ReLU is one of the most popular activation functions for artificial neural networks. Other functions are logistic sigmoid. It's the tradition kind of so far to use ReLU. So we have right now the layer that we want to build, which has a convolutional 2D, and then ReLU, and then max pooling 2D. Let's see if we apply our tiny neural network here, what will happen. So that's from Torch. We imported Torch, we imported the model, neural networks, and then the models. And from there, we define a class of our simple intracranial hemorrhage neural network. First thing, we define this convolution layer. So we have a 3 kernel size. It takes 1 channel and takes 16 like batch of 16. Then we have the ReLU, and then we have the max pool 2D with the kernel size of 2. This will send to the next layer, and this will send to the next layer. And after that, we have the global average pooling, the final layer, and then the final classifier. So this is the forward pass, and then we have the loss function that we will use once we have the training to know if it learned or not. So let's just run this. Nothing should happen. So I had to restart the whole session again, and then we're rerunning the whole thing. Okay, I think we have it. Okay, so now we had defined the tiny neural network that we created based on our current understanding of how convolutional neural networks should be built. And now it's time to introduce ResNet. So ResNet is a shortcut for residual neural networks that was introduced by He et al. Paper, Deep Residual Learning for Image Recognition. It is apparently one of the smallest members of the ResNet family, and it has many layers of convolutional stages and composed of what is called residual blocks. So ResNet, there are two ways of using it, and the one we're doing it is just using the architecture of the ResNet without the trained one with weights. It was trained on ImageNet, so we can benefit from what is called transfer learning. So you train a neural network on seeing things, and then you have the weights, so it is more used to images, for example, and then you could use it for your task. But for now, we're just gonna use this residual blocks ResNet architecture and define the forward pass. So now that you have an imagination of what a convolutional neural network, so like our toy dummy and convolutional neural network, just give us like an idea how each block is structured, but the ResNet is just like using the architecture and plug it in and see what's gonna happen. So we define it right now, nothing should happen, but we have it. And now we could start with the training, but let's do some sanity check. So we have the simple model, we can call it with this function, and then we have the ResNet model, we can call it with this function. So let's get a dummy input, like 4 slices, 1 channel, each image has this dimension of height and width, and see what the output would be. So yeah, we have an output of torch.size 4, which is the expected output that we want. So we could start with the training. So before we go into the training of the neural network, I thought that we touch on the training, like what do we mean by training a neural network? How does the learning in the neural network happens? So to do that, let's contrast again the biological neuron with an artificial neuron and see if we can bridge the gap between both of them. So this is from Wikipedia, a drawing of a biological neuron, which is a single pyramidal neuron. And you can see these are the dendrites, and this is the soma or the cell body. And then you have the axon. So the input comes in here, the neighboring cells, neuron sends a signal from the axon. So if you have neurons near each other, the idea is they learn, they start working with each other better if they're firing together. So this is the concept of neurons that fire together, wire together. And this is like from the 1949 by Donald Hebb, which is referred to the Hebbian theory of learning. Neurons that are doing something together, basically, the more they do that, they learn by strengthening the synaptic connections. That's the basic premise of how biological neurons learn. This architecture, again, inspired the neural networks. So you have the perceptron here, which is a single or very basic single artificial neuron, and you have input and then some processing in the node and then an output. How does this learn? This is like the basic, very basic unit of it is a linear function where you have y equals x multiplied by w plus b, which is the bias. So the w is what gets learned in the neural network. So if you stack more of those neurons together, you end up with a neural network. And this is the ones that we are training right now. So if you have, this is an input layer, and this These are the hidden layers that we are building for the ones that we spend time describing, the convolutional and then max pooling and so on. So you have those hidden layers, and then you have an output layer, the basic way of looking at it. So these are one neuron stacked together, and then you have different, for example, if we have 3 layers, you have 3 layers of those. And those arrows are the weights. So those are the synaptic connections that we have seen in the biological neuron, and represented by the weights. So the idea is you're trying to figure out, like in our case, if we have slice of a CT scan here, like as an input, so and then we have an output. Does it have bleeding or no bleeding? So what we have a supervised learning task right now. We have a supervised learning task, which is we have a data set that is labeled with, like, each slice is labeled. Does it have a bleeding or does it have a hemorrhage or not? And then what we're doing is we're training this convolutional neural network, this network, to learn the patterns that are in the input, like to map the statistical patterns to an output, which is hemorrhage, no hemorrhage in this case. So it goes through the first pass, and then we calculate something called the loss. So you're comparing the output to your predictions. And if that loss is too big, then the network did not learn enough. Then you want to move in a direction where it reduces an amount that it reduces this loss. So to do that, there is something called gradient descent. So it just describes the movement towards the local minimum. And then after that point, you go up. So you need to go to the point minimizes the loss. At the core of it is a derivative, like from calculus. But if you're dealing with multidimensional matrices, then it gets very computationally difficult. So there are now optimizers, like the Adam that we will use in our network. And this is basically a stochastic gradient descent. You reduces the loss, and then you correct the weights with something called backpropagation. Once you have the weights that like reduces the loss the most, then the network basically learned the statistical patterns that are in the input and managed to map them to the output based on this supervised learning thing. And then you have to be careful of things like overfitting and even underfitting. We have a video about that, previous video from the clinical AI rounds, you can check. But this is the basic premise of how a neural network learns. So as you have seen, like most of the architecture, I guess this is interesting to kind of point out, which is that most of the architecture is there. You're not gonna need to invent, but you need to kind of have an intuition what is going on. I think the most like you've seen, like we did a lot of pre-processing, a lot of data handling, and there are usually teams just like doing the data curation and the pre-processing, and then using those libraries, built-in libraries, to prepare the data for the training. So you understand with medical images, you have this class imbalances, so you have to deal with them. And for the training itself, the architecture is there. You don't also need to kind of code from scratch. It's there, and we can use it, build on the like work of others, stand on the shoulders of giants, kind of. The real work is after like this is optimization, making your training better, and so on. So that is tricky, but this is something that where most of the work is going on right now. So this block of code imports like the optimizer, the neural network module, and so on. And then like this is for measuring the area under the curve. And then here are the hyperparameters. Those are the things that you could change like later on and see, like increase the number of training epochs. Like how many times do you want the model to be trained from 5 to 10 and see what happens. Increase the learning rate. Like here you could say use ResNet or use the dummy one. So we'll start with the dummy one, the toy neural network that we have. And here you could mention, okay, should you use the ResNet that is trained already on the ImageNet, and see if it will make any difference. For this tutorial, we'll just compare the toy neural network that we have to the ResNet and see what's the difference. Here it just goes through the model, deal with class imbalance in the dataset that you have seen. We have very few that has bleeding in it, but most of them are normal. Most of the slices do not have bleeding in it. And then we use for the loss function, binary cross entropy loss function. So that's the shortcut for that, binary cross entropy loss function, which is just a loss function. Like if you're familiar with the mean squared error loss function, it's a simpler way from the binary cross entropy one. But just to understand it, is what you're doing is trying in the mean squared error, you're trying to see how far are your predictions from the truth. So, and then trying to minimize that. So we want this loss to go low. We want the accuracy to go high and the area under the curve to be high. We want a function that tells us how far are the predictions of the model from the ground truth. And this is giving us this value. And then we're using an optimizer. You could look it up. There are different optimizers. We're using Adam as an optimizer. And this is where the training happens. So this is the function that does the training for one epoch. And then we loop for 5 epochs. After the training is finished, we have like a loss based on the loss function that we have, and then we evaluate how good that was, and we have the accuracy and then the area under the curve. So, and then here is the loop for doing that. So it calls that previous function in this loop and then print out the loss for the training, the validation loss, the validation accuracy, the validation area under the curve. Those are the most important ones that kind of tells you if your model is learning, it's not learning that much. So let's just run that and see what's going to happen. So if this run, we will be training our toy neural network, starting. And this is a warning we don't need to worry about for now. So the first epoch is done. You can see loss is 1.17 for the training. So only on the training data set, which is 80% of our data. The validation loss is 1.17. Accuracy is 0.15. And then area under the curve is 0.6. So it was fast. Our network learned and our toy network learned. Let's go through it. It's interesting. So let's look at the validation loss. We want it to decrease. It is decreasing, but like not a lot. So we don't worry about the training loss. It's okay. You can see it's also decreasing, but like the validation loss is kind of like you're testing the validation that we took a portion of the data that the model does not see while it's training, and then we see okay how it performs. Optimally, as I mentioned before, you want external testing that the model never saw before, but we don't have enough data and we're doing it on slices basis, so we want to avoid this leakage kind of thing, and we can do it on a patient's level, but optimally you want to do it on patient's level. Anyhow, so loss is decreasing. This is good. It's learning. Accuracy was started with just almost nothing, like 0.1 accuracy, but then jumped to 0.7, then went to 0.6, then decreased, then increased. So you could see the accuracy is fluctuating from one epoch to the another. And this is the issue that this network was not able to deal with this imbalance, I guess. So it's saying, okay, like most of what the images are normal. So if I just like say normal, then I will be okay. I'll do okay. And that's what it did. Like, okay, most of them are normal. So the accuracy, yeah, it increased, but it did not mean that it learned. And how do we know it did not learn? Because the area under the curve, and let's just look at the area under the curve. So the area under the curve, you want like which is plotting the true positive as the false positive rate, and then you want it to be 1. Like if 1, then it's always your model does well, like telling which cases are really have bleeding and which cases do not have hemorrhage in them. Optimally, you want it to be around 1. So this currently right now our area under the curve is 0.63. So it looks like something like this. So it's not really doing well, but if you bump it up, you want it to be more like that. So these are the results from the toy neural network that we created. And then let's retrain, but using ResNet. ResNet now without the weights from the ImageNet. So just ResNet as an architecture. All right. So you could see now it's a different situation. You have the validation loss also decreasing, but decreasing this time more than the previous one. The accuracy started again low, but it increased, then decreased. So still, but not I guess the variation is not as sharp as the previous one, so we have more solid kind of consistent performance. And then the area under the curve, which is the most important, is increasing, and it reached to 0.87. So let's go back. It's like around 0.9, let's say, so it would be like this. So ResNet learned better and than our toy model, and is doing a good job. So right now let's do some inference, like plot the images and see if the ground truth and the predictions of our model, how do they relate to each other. We're going to import from the library matplotlib polyplot just for the plotting, and then we'll do some inference, like showing the validation, what was going on, like just pick some random validation indices like slices, take 16 examples and show the ground truth and then the predictions of the model. So we have, as expected, 16 images or 16 slices. You have Y, which is the ground truth. Y0 means no bleeding. And in this image, we have a probability, like the model says, okay, I don't expect any bleeding in this case, or I don't see any bleeding in this case. The same goes for here. The ground truth is 0. The model probability of having a bleeding in it says 0.01, which is very low. So it's consistent with the ground truth. Like in this slice, again, the same. This is the same. This is also 0, almost 0. 0, almost 0. So it's actually doing good here. It says like, okay, there's bleeding for this one here, like there's bleeding. This is the ground truth of bleeding, and then probability says yes, there is bleeding, almost 1 also. Here it made a mistake. The ground truth says it is bleeding, but the probability is not bleeding. It's wrong basically here. Right, this is like the bleeding here, but the model did not pick it. Here there's no bleeding. The model says there is bleeding, but not confident about it. And the same goes for here, where you have no bleeding, but the model is saying yes, there is bleeding, but not confident about it. What we could do next is, as I mentioned, which is the last part of this tutorial, is use GradCam, which is like a technique for visualizing the slices and seeing what the model, which voxels the model used to kind of make its decisions. So let's see. Right. So here the model says there is no bleeding, and the real ground truth is also no bleeding, while here the model thinks there is a bleeding in this slice, for example, with an index of 406. The ground truth is no bleeding, but the model thinks that there is bleeding going on, specifically in this region, so probably mislabeled bones as bleeding, because bone is high density. Here the model thinks there is a bleeding, and we can see those are the problematic voxels. Somewhere here, for some reason, it thought that there is a bleeding. Right, so with that, we finish our tutorial for today. So we have prepared an AI or a machine learning or a deep neural network, convolutional neural network that tells us if a slice of a CT scan has bleeding in it or not. Thank you for joining me. You have seen like sometimes I faced like errors. What would I do? I would go like and take that error and just ask Google about it or ChatGPT about it and see what to do about it. Sometimes I knew what to do, but I needed to make sense of it. Also, like coding, it should not be the obstacle. Just having the idea and going through Kaggle, getting familiar with this data sets. I personally found the most daunting task is loading the data set and pre-processing it, and then other things you can find out and you can build and you can understand and so on. So what we did, we loaded the data set, we used those data loaders, and then we introduced how the visual system works and then how convolution works, and tried to contrast both of them, and trained the neural network, built a dummy one, then used ResNet 18 then trained and visualized. So the differences, try to make sense of loss, accuracy, and why accuracy is sometimes not sensitive, and why you need area under the curve. And then we used visualization technique like heat maps and GradCam to kind of look at the data and see which boxes were problematic. I'll leave the link to this notebook in the description, and see you in the next one. Thank you.